right, folks, let's get started again because we got a sharp lunch date. So what we're going to do is we're going to move the hands-on part of this to this evening study session. So we're just going to have the lectures this morning, and we're going to move the actual programming part to this evening over at UT. Okay. All right. I need one more volunteer to run microphones to the questioners so we can hear what people are saying. You'll get an extra muffin from the break if you're willing to be a microphone runner this morning. One more volunteer.
You have one.
All right.
Oh, okay.
Okay, so Bibek is going to tell us about error mitigation, part 2 of this morning. We have a sharp deadline of noon for lunch because they're bringing our food, and then we'll continue on this evening and over at UT in the study session. So, go.
Yeah. Okay. Hi. Can everybody hear me? Especially people all the way in the back. Okay. If you have to. Okay, you can hear me. Good. I will be talking about error mitigation and suppression. As you can see from my lightly colored slides, that my slides will be different from Nick's. I'm not using my slides. So this is what was covered in the previous session, where he tried to tell you how you take certain Hamiltonians, map it to the device, and so on. And now we are going to go into the execution mode. So I'm kind of going to be Hamiltonian independent. I'm just going to assume that you guys are motivated enough to know what Hamiltonian you will be implementing and what problems you want to solve and so on. Our job really here is to figure out how to get the best results out of the device. Error mitigation and suppression kind of lives very close to the hardware without really touching it. So we are going to be really low level users. Like you can kind of think of it like programming in C maybe, right? You really want to know how the device works so that you can make it work the way you want it to, right? And there are two different topics I'm covering, error suppression and error mitigation. They're kind of related, but they're also different. I will try to explain what we mean by these two rather similar sounding terms. Error mitigation is generally explained as something where you have to do certain post-processing in your results, but that's not quite right in the sense that you also have to choose what experiments you are going to do in order to do the post-processing. Generally, there is a calibration step, a step where you're trying to learn about the noise in your device. Then in the second part, you do various experiments that are kind of similar to the experiment you want to do, but at different conditions, and maybe you combine them, okay? So it's not just post-processing, it also kind of gets into the experiment design, okay? So I'm again going to go back to one of the slides that Nick had, where he was talking about the portions he talked about, and really the error suppression and error mitigation are the two things that I will cover. I will go through in error suppression, dynamical decoupling, and Pauli twirling. The twirling idea will come in later as we talk about probabilistic error cancellation and amplification. I will also talk about measurement error mitigation and zero noise extrapolation. These seem like these are different topics, and when you start talking about them, the math seems kind of different. But at the end, we have to combine all of these, right? So the entire lecture will have this theme where we start kind of complicated, but that's because we want to make our life simple. And so things will be complicated at certain places, but that's okay. Don't get disheartened. Just to clarify the different error something terms, which sound like they are the same thing, even though they have technically slightly different, technically quite different definitions. By error mitigation, we mean this post-processing thing I talked about, where we learn about the noise of this in the system, and then we try to mitigate it somehow. Error suppression is about not letting the noise happen at all. You just suppress the noise before it even occurs. And of course, you can do that at the level of designing your devices, but we are considering what we can do as a user, okay? Error correction is not something we will talk about. Error correction is closed loop in the sense that you have to first detect the errors, then figure out what you want to do. After having detected those errors, you will want to correct them and so on. It has quite large resource overhead, and it's a long-term view of like where we want to get to eventually. Error mitigation, error suppression are what we are doing in the short term. That doesn't necessarily mean that it will have nothing to do with error correction once we get there. We might need error mitigation and suppression to be able to enable error correction, but these are things we can do right now. In terms of the resources, that's something I want you to keep in mind as I describe the processes, like what is being required either classically or in the number of qubits or in the number of gates as we describe these various methods, because that essentially determines what you should be using and what you should be avoiding when you're running your experiments. Right? There are going to be certain resource overheads. Error suppression has generally low resource overhead, but when you include the fact that you're running this on a device that also has a classical post-processing step, you will notice that that's not always the case. Error mitigation generally requires more number of runs, so the runtime increases, but not necessarily number of qubits. And hopefully that statement will make sense by the end of the talk. Open loop basically means so imagine you have your quantum computer, you're detecting your errors, and then you do something about it. You do some if statement or something. So you're closing the loop, right? Open loop means you don't have to do that. In error suppression, we don't even detect the errors. In error mitigation, we do detect the errors, but we do something after. We never go and do something to the quantum computer having detected the errors, right? So there is going to be no loop, and that's why I call the first two open loop, and error correction is going to be closed loop. Error detection with some kind of post-selection would be a open loop, right? To motivate this further, by the end of this talk, you should be able to understand this figure from this paper that came out in 2023, the evidence for the utility of quantum computing before fault tolerance. It was featured in Nature's front page. And hopefully this figure will make sense. So this is the motivation for the experimentalist, is that by the end of this talk, you should understand what's going on in this figure, okay? And for the theorist, I have a different set of motivation. By the end of this talk, you should be able to understand all these equations and how we go from lambda tilde to lambda, okay? And we'll try to go through these step by step, try to understand why lambda tilde is actually more complicated than lambda, even though that doesn't look like the case, but it is. Okay, let's jump right in to the first error suppression technique. And as I said before, it will seem a little bit disparate, but keep your motivations in mind, whether you are a theorist or an experimentalist, and we'll be okay. Before I describe what dynamical decoupling is, let's just consider a very, very simple example. You have a Hamiltonian, it's a single qubit Hamiltonian, and there is some bath. I know nothing about the bath. I'm going to break down the Hamiltonian into three pieces: the one that only acts on the system, one that only acts on the bath, and one that acts on the system and the bath together. I'm going to assume that the system is not evolving at all. HS equals 0. HB, I don't care about. Something is happening to the bath. I have no control over it. HSB can always be expanded using that equation above, even though we know nothing about the bath. It could be infinite dimensional system, doesn't really matter. Now consider the free evolution under that Hamiltonian, which is going to be e to the power minus IHT, HSB and HB combining to give you H. And I sandwich it with 2x Paulis. What is going to happen? Well, if you look carefully, there are going to be these two minus signs that showed up, right? Sigma y has a time reversal and sigma z has a time reversal. That is because I sandwiched it with x, and y and z anti-commute with x. X commutes with x, therefore nothing happened. That is equivalent of saying, let me do a free evolution, but in the beginning and the end, I'm going to do an x pulse, right? So just by doing that, I have introduced time reversal in two of the terms. Now, if I follow that with the free evolution here, those two terms are going to cancel, right? Because for half the evolution, I had minus signs in front of those terms. And for the other half, I had a plus sign, it cancels. So by simply doing this x-free evolution, which is essentially very similar to the echo experiment, spin echo experiment, I was able to cancel everything other than the sigma extra. You can generalize this idea from spin echo to say, okay, well, what would I need in order to cancel everything? Okay, turns out you have to essentially symmetrize over the Klein group, which in this case is shown right here. I sandwich my free evolution with identity x, z, and y, right? Each of them is going to give a certain minus sign to certain terms, and then when I sum them up, everything gets canceled. This kind of idea of symmetrization is quite necessary to understand both error suppression and error mitigation. So, look carefully. Okay, any questions? Because this, I do need to make sure everyone understands. Yes, you go first, sure. What is what? X is the Pauli X. Yeah, I'm using both sigma X and Pauli X kind of because when it's up in the Hamiltonian, I make it sigma, and when it's as unitary, I make it X. But for your situation, it doesn't matter. You had a question? A client group is just I, X, Y, Z. Pauli group also has the plus minus I you have to take care of. So it's kind of like the Pauli group, but without the signs being considered. Yeah, sure. This is just a statement I'm telling you. Like, I'm literally telling you, if you do this, then it essentially ends up being the XY pulse. So if you have ever heard of the universal XY sequence, I'm just telling you that it's the same as symmetrizing over the client group. Okay? Yes. Mm-hmm. Yes. Just to simplify, you can make things much more complicated. You can really make things much more complicated. Yes. Oh. Oh yeah. We do have some microphone runners. You got both.
So for the free evolution, we're only looking at the interaction term because that's what we're interested in. That's why the whole Hamiltonian has also the Bath term with the index for the identity for the system. But
Yeah.
because we're interested in interaction, that's the only.
Yeah, we only in this particular case care about removing interaction between the system and the bath. Whatever happens to the bath, we don't care.
Okay.
And this scheme is not really going to do anything to the bath. Okay. Okay, so then let me give the general description of what dynamical decoupling is. You have some kind of a free evolution, and we're going to puncture this evolution with a series of pulses, and that is what dynamical decoupling is. Of course, if you do it arbitrarily, you put like some pulse after a certain duration and different pulse after a different duration. It is, and as long as all of these pulses multiply to identity, it would be a dynamical decoupling sequence, but what kind of errors it cancels can get somewhat complicated. But that is the general description of dynamical decoupling, and people have gotten quite creative with the kind of sequences you can come up with. You can say, okay, I don't want to set HS equals to 0. Maybe I want to combine it with some kind of quantum error correcting code. Maybe I want to make sure that my pulses are imperfect and I want to cancel those. Really, like, there has been like 20 years of work on dynamical decoupling, and things can get quite interesting. But for our purposes, let's just figure out how we implement them on a real hardware. So let's say you wanted to implement this XY sequence, also called the Eulerian DD sequence. The way you do it on the hardware is you just apply an X gate, include some delay to be able to capture the gap between the pulses, and that's it. It was not going to be the same as the theoretical limit where these pulses are delta function like pulses. You're going to do it with some kind of a Gaussian pulse here, but it has been shown that it actually still does work, even though it's not going to work perfectly. It actually still works in terms of canceling the system bath interaction. Okay, so implementing DD, quite simple. How do we do it? You have some kind of a circuit. You figure out exactly where the gaps are, right? And you figure out what DD sequence you want to implement. You find all of those gaps. You just put your pulses. Done. Very, very straightforward, right? Really, the only thing that you have to worry about is, okay, what are the pulses? What are the gaps? Do I want to put them in certain places? Maybe I don't. Those are things that all you can, keep fiddling with. These are hyperparameters, okay? But turns out that some very, very simple sequences like XPXM, X positive, X negative, which is basically very similar to the XX sequence, but you're just choosing the orientation, seems to be quite effective. So, yes. Yes, those are pulses. In this case, I'm considering them to be single qubit gates. You can do DD with multi-qubit gates, but there are very few examples of them working quite well. Oh, the question is, what are the P1, P2, P3, P4? Are those the pulses? And the answer is yes, they are single qubit gates that I'm using as pulses here. You could use 2-qubit gates as your pulses, but you're going to get farther and farther from your theoretical description where 2-qubit gates are going to be very long in time. Yes.
So I'm trying to understand what is the overall goal of this? Like, are you trying to like mitigate the error of like
I'm trying to suppress any system bath interaction term that might be affecting me during the free evolution by essentially doing this symmetrization procedure by applying dynamical decoupling. So whatever errors you would accumulate some kind of errors just by doing free evolution on a single qubit. It might also be that you might have some kind of a crosstalk between whatever gate you are doing here and its neighboring qubits. And so DD sequences will also cancel that. So we're essentially trying to cancel all kinds of unwanted evolutions, which you expect the system to sit still, but the system is not going to have Hamiltonian zero, right? So that system math interaction term is what we're trying to cancel.
So like you leave one qubit alone for some time, and you're just trying to mitigate the error that
Whenever that happens.
Yeah.
If you in your algorithm, if you have a qubit that is sitting idle, then that is the place where we would insert dynamical.
And so you're saying the trick is to give it these pulses that
Yes.
fix it.
Yes.
And the choice for the pulse is given by like a model of the type of
Yeah.
noise that is going to be. Okay.
Yeah, but for single qubit, this is universal. For single qubit XY is universal. You could go to 2 qubits and things can get more complicated.
Okay.
But how do you choose the pulses is like, that was my whole thesis. So.
Okay. Thank you.
Yes. Uh-huh. Oh, where? This one, the pulse?
Yeah, yeah.
Yeah, that's time.
Okay, it's time.
A time in DT, some unit of
That's
time, which is like 10 to the power minus, what is it? Like that's right.
Nanoseconds. Okay.
The 0.222, it's like 11/9 or something. Yeah, that's that. Yeah, 9/2. That's right. Oh, sure. On the x-axis, you have time. Here are a bunch of qubits. These are gates. So it's like a circuit diagram, but I've expanded the circuits to be, the gates to be rectangles, not squares. So you have a CX operation that is happening here. And then these are all the idle times, right? And so CX operation takes longer than the Hadamard, and therefore the gate times are different. So it's essentially a timeline of the circuit. Okay, it's a circuit diagram, but a little bit more information than that.
Qubits, right? So for
Yes.
this CS, why there's only one column?
Oh, here
so
down
one
here.
row. Okay, okay. Oh, I see.
It's always connected to the other one. Another question? Who wants? Go ahead, and after that you can go.
So basically, what this whole circuit is doing is it's trying to perform CX gates on certain qubits, and during the idle time, you apply 4 pulses to symmetrize so that it doesn't have any additional phase factor.
And any additional noise, yes.
And at the end of it, you compare all the qubits that had the idle time and didn't have the idle time to see if it actually canceled out all the additional phase factors.
Yeah, the circuit is random. I just picked a
Ah,
a random circuit. Like, yeah, I think it's like a GHZ circuit with some H at the end or something. Yeah. I'm not gonna. Sorry. Oh, more questions. Yes.
Yeah,
Yes, sir.
I'm still, can you please go back
Yes,
to
yes,
the
yes.
same slide? So for example, I'm talking about the one in the middle, and
Uh-huh.
there are some phase passes before and after, okay?
Uh-huh.
So I have one set on the left, one set on the right. Why do I have only one set for after the first gate
Uh-huh.
and
2 sets in this.
before the last gate? And for the MT3 qubits, so I mean, why didn't I use more of them in order to fill the time? Because the time of a single operation like B1, for example, it should be fixed for all of them. So if I use B1 and it's like whatsoever, like 1 second, well, 1 millisecond, and then I use it in the second qubit, it's 2 of them. and then I use it
Yeah, yeah.
for everyone. So why didn't I use more operations instead
Yeah.
of using just a very minimal set for, especially for the ones like the last 3 qubits where there are no operations
You could
at
do
all?
that. You could do that. You could
Oh.
use more operations. You could use less. We have known after, like, there is a this paper in the second slide basically explores that question. What is the right amount of spacing you want to put? How many pulses you want to do, and so on. Theoretically, you should be doing as many pulses as possible. But on the device, it's basically a hyperparameter. You have to figure out how much noise you cancel, how much noise you introduce by doing the single qubit gate. And so, you can play with it
Okay.
endlessly.
So is there
Yes.
a minimum and maximum number? Like, is there an equation in order to be able to know whether I'm doing it in the right way or not?
The minimum number would be like, you either do 2 pulses or 4 pulses. 2 pulses, you need to cancel just Z-type errors, XP, XM. If you're trying to cancel all single qubit errors, you need at least 4 pulses. But then as you get more complicated, things get very, like, there's so many things you can try. And actually, in the next slide, I will show you my solution of how I deal with it.
Thank you.
So great question. There's a lot of DD sequences, okay? And we basically wrote this paper where we considered like 60 plus DD sequences, various time gaps, try to exhaustively understand, okay, what is the best way of doing it? Theoretically, there are certain answers, but once you include the single qubit errors that get introduced and so on, things get very complicated. So my solution is something we recently put out, where we essentially use some kind of a genetic algorithm to test a whole bunch of different strategies and then just let them compete with each other. And whichever one works best is the one that works best. Because I think there are too many hyperparameters here. Either you have something very, very simple that works quite well, like just 2 pulses, cancels crosstalk and so on, or, you go crazy. And some people have tried to throw machine learning at it, and it does very well, but then the sequences that you learn don't really work well later. So, it's a question of how much resources you want to throw into trying to optimize this thing. You could keep optimizing it, but, there is also the resource consideration, right? How much time does it take? So this is something that we came up with, and it seems to work quite well. You just take a certain target circuit that you want to implement, you figure out a training circuit from that, use some kind of classical learning algorithm and some optimization function to train the right DD sequence there, and then spit out the sequence that you want. So consider all kinds of things. How many pulses, what should be the pulse gap, what should be the sequences, and so on. And seems to work quite well as long as you use some parallelized learning scheme like genetic algorithms.
Do you take into account different error rates on different qubits?
The issue with dynamical decoupling is that it only works with non-Markovian noise models, and non-Markovian noise models are extremely hard to characterize. So oftentimes what happens is dynamical decoupling is the first thing you do in order to get the simplified noise model that you want. So if you're using Qiskit and you're simulating your device in a certain way, if you use dynamical decoupling, it doesn't improve the performance. Why? Because the rates you got itself was after doing all kinds of averaging from the error suppression. So error suppression is really step one. Okay, the error rates actually kind of only make sense after you do the error suppression. Okay, yes.
So like Qiskit backend, like transpiler, at what stage does Qiskit do this, or do you have to do it?
If you set optimization level 3, then it will do it, or you can also turn it on and off. That is something that we'll show in the notebook, how to turn it on and off. Okay, but there is like for a lot of these things, there is just a standardized way of doing it. We are rather just going deeper into trying to understand why we do what we do. Yes.
Maybe what do you do if you have non-Markovian errors first?
Like, what do you do if you have non-Markovian errors? Like if like the time is involved in those type of.
That is something people have looked into, but I don't think we have a great answer to that. You can try to do error suppression. You can try to either do twirling or dynamical decoupling to address that. But I don't think we even have currently a nice scalable way of capturing all the non-Markovian errors.
Do you have like kind of a bound error for that ones, or just ignore it?
Generally, I think our latest devices, we are being able to estimate the errors quite well with Markovian models. So I think that's what I'll say, is that we are decent at estimating the errors. But there could of course always be non-Markovian models that explain it better than our Markovian models.
And kind of like complementing like what he said. Well, first of all, like Do you have like a specific model of non-Markovian, or you're just ignoring like it could be any non-Markovian error?
With dynamical decoupling, it doesn't matter.
Yeah, I know that it doesn't
Yeah,
matter, but
there is,
have you
I can,
characterized?
send you a paper that tries to come up with a non-Markovian model for the device, but again, it's not easy. I
And-
did it on 1 qubit and it took forever.
And maybe one last question. Sorry for giving
Uh-huh.
you so many questions. Like this is with the PB. I suppose that is a Bernstein-Basirani algorithm.
That is a different
This is what-
paper. There is a
Oh.
paper where we do in that paper we do show BV.
Okay.
So there are results on Bernstein-Basirani. These are the results on Bernstein-Basirani, where the genetic algorithm DD seems to do the best, and there are a bunch of other strategies we tested.
Which other algorithm are you also using here?
We tested it on Bernstein-Basirani and just mirrored randomized benchmarking, and it
Okay.
worked in both cases when we called it. But we have tested in other cases too, and it seems fine.
Okay.
Okay.
Thank you very much.
Yeah. Okay. So with dynamical decoupling done, we will move to twirling. And twirling is essentially what is going to allow us to start from a very generalized description of the noise model to say that what we have is a Pauli model. Okay. If you look at lambda tilde, it has 2 coefficients. P alpha and P beta are Paulis, but there are 2 coefficients. Okay. The whole simplification process is that you go from 2 coefficients here to just 1, and that's a rather large jump, because any noise model can be written in this Krauss operator form. And in order to go here, you're essentially assuming that the Pauli transfer matrix has only diagonal terms. Okay. And so how do we do twirling? I'm going to give you a very simple single qubit example, and hopefully that will help explain what's going on. Let's say I start with some noise model lambda on a single qubit, right? And I write the Pauli transfer matrix, where Pauli transfer matrix is essentially just prepare in some Pauli basis, apply the noise channel, measure in a different basis. Okay. And so it has these terms. Imagine if I sandwiched this evolution with identity X, Y, and Z, and I'm going to color the diagonal terms orange so that you can see that they don't change. And you'll notice that if you consider all of these, each term essentially gets 2 negative signs and 2 positive signs, okay, in the 4 different cases. Okay. So if you sum them up, you're going to get all the off diagonal terms to go away and only the diagonal terms to remain. Okay. This is how you would twirl in a single qubit case. What does that mean? That means you take a circuit and you simply repeat it 4 times, each time, sandwiching it with either I, X, Y, or Z, and then you take the average result that you get from these 4 circuits with the probability of sampling from each of them being equal. Then, it's not that you have a circuit that has this noise channel. It's just that if I average from those 4 and I sample classically, then the resultant channel can be essentially described as this. Okay. So you can see this is kind of similar to dynamical decoupling, right? In dynamical decoupling, we were doing that at the Hamiltonian level. Here, I'm doing it at the Pauli transfer matrix level, but the idea is very, very similar. And so how do we do it for maybe I can go 1 slide up and show you this one, which is the connection between dynamical decoupling and twirling. In twirling, we essentially were taking some group and then sandwiching the noise channel with that group and then average over it, right? In dynamical decoupling, you kind of do the same thing, but it happens up here where you have a product and you have some group and then you sandwich the Hamiltonian with that group. And so if you use the BCH formula of 2 first order, what is going on in both cases is symmetrization. If you think about it in terms of some general group, in dynamical decoupling case, that is called a decoupling group. In twirling case, it's called the twirling group. Surprising. Yeah, so this is a very cool thing that you can, of course, go and read more about. But let's go back to twirling and how it is done on the device. So we know that what we want to do is we want to take some channel and append some Paulis, do a whole version of that channel. We considered the case where there was only some error channel and there was no unitary being applied after. But what happens if there is a unitary being applied after? Well, if you know how the unitary transforms the P, which is P of U, P followed by U gives the same as U followed by P prime, then you can again sandwich lambda by essentially making P prime commute through U, right? So that gives you a description of how you want to do twirling. So consider this circuit right here. I want to twirl this circuit. What does that mean? I want to create another instance of that circuit, but now there are going to be these random Paulis that are going to be sprinkled all throughout the circuit. I decide to use the Pauli XXXY. I commute it through the C naught. So this XX becomes XI. Everything remains the same. I do a different randomly chosen Pauli here. Again, this XX becomes IX because of the C naught. And now I have a different circuit, which is equivalent to the previous circuit, but now things have been twirled. And you essentially want to do it as many times as you want to twirl, right? So ideally, we said we want to twirl an entire group. That is going to be difficult. So we're just going to randomly choose a whole bunch of Paulis, right? And create different circuits for them. So let's say you had some circuit, you wanted to run it 100,000 times to get the statistics. Now you could say, no, I'm actually going to run 100 different twirls, 1,000 shots each, right? So in some sense, the runtime didn't increase. Although if you have a IBM account and you try to do it there, you'll be like, no, the runtime definitely increased because there's also a classical pre-processing step necessary where you have to take each circuit and transpile it and so on. So 100,000 shots on one circuit is not the same as 1,000 shots on 100 circuits that are equivalent. So in that sense, error suppression does have a cost, but in a different sense, just looking at how many experiments you had to do, there was no cost to doing Pauli twirling, right? And what did we get out of it? What we got out of it is that our noise model became substantially simple and also suppresses coherent errors. Okay. Oh, there's a question. Yes. Mm-hmm. So the question is if we are uniformly picking from the random set of Paulis,
Yeah.
then yes.
Okay.
Yeah. We pick uniformly. We just want to make sure that these are native gates. So we are not considering like, that's why you consider Paulis, right? You could have considered like some other set, but then that was going to be hard to implement. You get to the depolarizing noise after. The initial channel does not, initial channel is too general. After that, you get to something that is not exactly a depolarizing channel. If all these terms were exactly equal, right, then you would have a depolarizing channel. But here you have, I term, X term, Y term, Z term, right, for a single qubit, for example. Now, if all of those terms were exactly the same, that would be a depolarizing channel on a single qubit. So it's not a depolarizing channel, it's a Pauli channel. Okay? Yeah.
Paulis around the signal gates in one side different.
Oh, because you want to consider a unitary and it's a imperfect unitary, right? So we assume that the imperfect unitary is the perfect unitary times some noise channel lambda, right? And we want to twirl the noise channel, but we don't want to affect the unitary. So what you want to do is P lambda P U, right? But P has to now go through U to get to the other side and it becomes P prime. So what you really want to do is XX lambda XX C naught. But in order to do that, we're going to make the XX commute through C naught, and that's why it becomes XI.
Okay, thank you very much.
Yeah. Okay, now that we understand twirling, we will go back to the big picture, and hopefully the first line makes sense. Okay, we started with some general noise channel where we couldn't really make any assumptions. And now, because we did twirling, we are going to at least approximate our noise channel with something that has a diagonal Pauli transfer matrix and has a simplified form that looks like that. It is not quite the depolarizing channel, as I was telling you before, but it is simple. The next thing we would want to do is assume that the channel has a Lindbladian description, which essentially means that it is Markovian, and dynamical decoupling and randomized twirling again will help with that, right? So both of these things are kind of covered by doing error suppression. Now let's move on to error mitigation. And again, I know it seems a little bit disparate, but it'll all hopefully come together by the end of it. So to give the simplest description of error mitigation, I've chosen the simplest error mitigation scheme. This is more for educational purposes than anything else. Let's assume that our entire experiment is perfect. Okay, the only error comes from the measurement. Measurement is the only thing we worry about. And measurement has some kind of a systematic error that we don't know what causes it, but we know that every time we go and run our experiment, there is this systematic error that you see in the measurement. What do we mean by that? Let's say I prepare the state 0, and what do I expect to measure? Well, I expect to measure the bit string 0 with 100% success probability, and I don't expect to measure bit string 1 at all. But when I go and measure it, 90% of the time it's 0, and 10% of the time it's 1. So clearly something's off, right? Something happened. Then I prepare 1. I expect to get 0, 1, but I actually got 1 only 80% of the time. So I say, okay, that basically captures my systematic error, right? So I'm going to write a response matrix M, which essentially tells me how my results were distorted. And so anytime I have a true result probability vector T, what is going on is that the measurement error is applying this distortion M, and I'm getting some probability P. So what should I do when I get a probability P? Well, just apply M inverse and you're done, right? What does that mean? Well, it means we basically have to run some kind of calibration experiment first, figure out exactly what our response matrix is, right? If you have n qubits, then that means you have to do 2 to the n different experiments and get a 2 to the n by 2 to the n matrix, which is M, which essentially captures my measurement error, right? For each of the different computational basis elements. And then whenever I run my actual experiment, I get P and then I apply M inverse. This both shows how error mitigation works and also why error mitigation is hard. Okay. First of all, instead of just doing the experiment, now you have to first do a different calibration experiment before it, right? So you have to make sure that you do that either before or maybe right after, as long as the noise model doesn't change. Second, this is a 2 to the n by 2 to the n matrix. For 100 qubits, that's going to be impossible, right? So even if you could completely capture a response matrix, you can't, right? So it also shows you that there is an exponential overhead in doing this, even in the calibration experiment itself. Okay, and so now we'll try to resolve that a little bit. How do we resolve it? Well, one thing you could do is you can just say, oh, you know, all the qubits are independent. There is no measurement crosstalk. Actually, I just need to do like 2 experiments per qubit. So it's not 2 to the n experiments. It's just 2 experiments, right? And I have a locally correlated measurement noise, and so things are fine. That's not as simple as you think, because what happens is even if your 2 to the n by 2 to the n matrix was just n 2 by 2 matrices, right? What is going to happen is, let's assume that you got like bit string 0, right? How do you know, how do you interpret that? Well, you have to multiply it with the M inverse of this rather simple matrix, but any bit string has a non-zero probability if all of these individual matrices M were not all diagonal, right? And so things are still complicated, but there was one solution that was proposed and seems to work quite well, which essentially says, let's reverse the entire ordering, where first we do the experiment, we get some kind of probability distribution, and then we figure out, okay, what portion of the response matrix do we actually need if these are the only bit strings that we actually observed, okay? And that seemed to work decently well. And that is one of the methods that now you can invoke. It's called M3. And if you're doing a sampler type primitive on IBM Qiskit, then you should be using M3. It incorporates the locally correlated measurement error mitigation, also does this subspace reduction whenever necessary. So it's quite good. For the experiment that we showed in the Nature paper, what they did was a different error mitigation technique called T-Rex. It has to do with twirling the measurement noise. I'm not going to go into too much of the details of it, but what I will tell you is generally how does it work, okay? Basically, I'm going to tell you how it works, but I'm not going to tell you why it works. For that, you'll have to read the paper. You essentially start by collecting your data in such a way that you say, look, I want to implement some unitary C, but I'm going to do a twirling at the end of it, okay? So instead of doing twirling on the noise channel, we want to do twirling on the measurement. And you just make sure you keep track of what P of Q gave you what bit string X. That's really all that this acquired data set is saying. Okay, run your experiment, just make sure you twirl, and when you twirl, keep track of the twirls and what the corresponding measurements is. After that, you can compute a fidelity, which basically means go through the entire data set, you collected Q comma X, Q was the twirl, X was the bit string, and just figure out whether you need to count it positively or negatively. So gamma SQ is going to be 1 or 0 depending on whether this particular Pauli commutes or anti-commutes with Z of S, which is essentially the Z observable with identities wherever there are zeros and Z's wherever there are ones. And there is also this bitwise addition of S comma X, where S was the bit string that you want to get the fidelity for, and X was what you measured, okay? And the entire technique kind of boils down to doing this for a random unitary, doing it for identity, and then just taking a ratio of the two. The identity part tells you how distorted your measurements are going to be. So then when you run the experiment, you just rescale with it and seems to work perfectly fine. So it's much simpler than the M3 method. And it's actually the default method now. If you're ever computing expectation values using Qiskit, it will just naturally do tier X for you. Questions? Yes. The question is, how do we know the errors are systematic? You go and check it. So you can collect it. You can get your response matrix, get it later again, right? So you generally, after the calibration cycle ends, your response matrix is no longer going to be accurate. Okay. But throughout the a calibration cycle, which is around 24 hours, the response matrices and the errors we get are going to be quite good. But it's the same question as like, how do you know your T1, T2 times that you captured are right? Yeah. I mean, you either have to know about the stability of your system, or if you're just a user, then you just go and do the experiment and test it. Okay. But generally, the measurement errors are quite stable compared to the T1, T2 times. Yes.
Doing the operation on the result of the measurement, but that's like a classical distribution depending on specific basis, right? Say there are two states, like we get the same classical distribution on that basis, but like they actually have difference in phase.
Yes.
So they might correspond to like different like original state, like for say a perfect compared to a fault tolerant computation. So like, why does this works? So I'm still not entirely convinced.
We are modeling the noise as a classical stochastic matrix, and we are simply inverting it. In some sense, it has nothing to do with quantum computing per se, other than the fact that we are doing it on bits. And in fact, a lot of what you're seeing here was already discovered or used in like since the 80s in high energy physics, where they have been using essentially like measurements from detectors and applying similar kind of techniques to get rid of the distortion. So measurement error mitigation is also known as like unsmearing or unfolding or something from high energy physics. It's just that we're doing it to bits.
Okay, so because the errors is mainly modeled in here is like stochastic
Yes,
kind of
exactly.
error. I see.
Yeah.
Thank you so much.
Yeah, it's just a simple way of capturing the systematic errors as a stochastic matrix, and we just invert it and apply it.
Yeah, gotcha.
Yeah. Yes. This one. This one.
So I want to understand the process of how. Oh, thank you. I want to understand the process of how you make this response matrix.
Mm-hmm.
So do you pretty much, so the steps at the top, do you apply every single measurement multiple times? So you measure like, let's say 1024
Yes.
times, calibration experiment 1024
Yes.
times, second experiment 1024 times, etc., right?
Yes.
In order. And then
the ordering doesn't matter because you're assuming that each experiment is identical, right?
And then you somehow average over
so
these
results.
results?
Let's say you do the first experiment.
Yes.
You're trying to prepare all zeros.
Uh-huh.
You do it 1,000 times, you get a probability vector. The probability vector says 0, 90% of the time, some other bit string, some other time. You just stack them up, make a probability vector, right? Okay. That is going to be the first column of your M. Just do it 2 to the n times, right? Don't do it 2 to the n times, but you do 2 to the n times and you get 2 to the n by 2 to the n matrix. Rather simple to do if you have like 5 qubits or something, but once you get to like 20 qubits, don't try it.
Alrighty, got it. Thank you.
Yeah.
Mm-hmm.
That's why we like T-Rex, because T-Rex, the paper is called model-free readout error, because here you don't have to capture the response matrix. You just care about what values you want to compute and then just go and try to get the distortion for those specific bit strings or observables. Yes. you have to assume that so the question is, do we have to assume that the error is going to be the same for every experiment? Yes, because if the error was changing, right? Well, at least if the probability was changing, right? Then it's not going to work. I mean, all of error mitigation is like that, right? You have to go be able to understand what your noise model is and then be able to do something with it. Okay? Yes.
So maybe you're gonna just talk to it later, but how does this compare to dynamical decoupling? Like dynamical decoupling explicitly, it works because you are basically suppressing like the
Yeah,
the HV, but this one you actually, I think you need to know something about the model, about the error model.
Yeah, so you see, error suppression and error mitigation, often they work on orthogonal components, like twirling was working on specific gates, dynamical decoupling was working in the gaps, measurement error mitigation is working in the measurement. It's just, we are trying to cancel noise throughout the device, and that's why it seems desperate. Well, we are desperate, but it seems disparate, right?
And
part of it is desperation because you're trying to figure out whatever you can do to cancel whatever errors, okay?
And in layers, like if you want to do like the most perfect experiment, like would you do first DD, then error mitigation, and the last error correction, or first, like what is gonna be the order?
You do
Like-
error suppression always,
Yeah.
okay?
Okay.
For whatever you do. Measurement error mitigation, you kind of do it at the end, so
Okay.
kind of doesn't matter. Error mitigation generally is done as a post-processing step. Error suppression has to be included.
Okay.
In the error mitigation. Throughout the whole process, you want to keep doing error suppression because you're simplifying your noise model every time you go. So you do want your measurements to be perfect for the previous step to work, right? For like, even if you're trying to like figure out whether or not my twirling worked, you should better remove your measurement errors because otherwise you're going to get a distortion. Yes.
If we bring fault tolerance to the picture, how can we insert dynamic decoupling with, I don't know, error correcting codes? Do we need to, we just apply it and that's it, or?
I will refer to the paper that John wrote a while back.
Okay.
Nung, Preskill, and Lidar have a paper called Combining Dynamical Decoupling with Fault Tolerance or something to that effect. So
Okay.
read that paper.
All right. I have another question. I mean,
Yes.
you said that, yeah, don't do it for 2 to the 10 or something like
To
that.
the end, yes.
But what are the limits of error mitigation techniques at the moment? What are the system
sizes?
System sizes, yeah.
I think they have been able to do it all the way till 127 qubits. And we probably want to do it to our entire device capabilities, 156. So,
Okay.
you know, we keep finding limits and we keep coming up with solutions, right? Even for the 2 to the n by 2 to
Okay.
the n matrix, we came up with subspace reduction. Then we came up with T-Rex. So, you know, you find limits and you find solutions.
Okay. All right. Thank you.
Yeah. Okay, let's get to zero noise extrapolation, which is something that comes up when trying to do probabilistic error cancellation and probabilistic error amplification, which is kind of a combination of the twirling idea and zero noise extrapolation, okay? The idea behind zero noise extrapolation is that if you have some observable that you know has some lambda that essentially tells you how it is going to be affected by the noise, which is observable in this case is scaled linearly with noise, then you should be able to figure out what the zero noise value was by simply scaling the noise. So by doing experiments that are worse, have more noise, you should be able to figure out what the zero noise value is. For something linear, you can, I'm sure this whole equation looks rather simple to you. We're just trying to figure out the y-intercept by taking 2 points. You can, you know, make a line, get the y-intercept. What if you had more than 2 points? Turns out you can do that too. Essentially, you have to solve this matrix equation right here. And, you know, essentially what you're saying is I have some kind of a Taylor expansion for my observable in terms of the noise parameter lambda, right? And I'm going to just use that Taylor expansion to figure out what the y-intercept is going to be. So I'm going to kind of skip this because I think the idea is rather straightforward. Plus, like generally, we only encounter the linear or the exponential fit. But the idea is that in general, you should be able to do this, right? You take your observable, write a Taylor expansion in terms of lambda, do various experiments at various stretch factors for the lambda, and then get back to the zero noise extrapolated value. And how many points you need essentially has to do with what polynomial you use to make this approximation. But, you know, the whole thing is possible. The terms you want to look up are Richardson extrapolation and Vandermonde matrix. This matrix is the transpose of the Vandermonde matrix. So if you're kind of curious about what this matrix looks like or does, you can look that up. The simplest way of doing zero noise extrapolation, which is where it was first introduced, was to simply stretch the circuit. I want to make my circuit more noisy. Let me just, and I want to do it very, very precisely. I want to make it twice as noisy as before. How do I do it? Just make the circuit twice as long using the exact same operations. That was the idea. That works decently well, but it's a little bit imprecise, right? Because you have these pulses, you have to flatten it. Maybe the pulse errors have been, and these pulses to do the gates are rather calibrated rather well to be able to be exactly what you want them to be at a certain pulse width and so on. So trying to scale them and then expecting that you're going to get like a linear increase in the error is not a great assumption, although it did work. And so the way we will do it is by using the sparse Pauli-Lindblad model, which again brings us back to this a particular slide. Okay, so we already got the Lindblad, we already got the Pauli model, right? And we want to get to the sparse Pauli-Lindblad model. The Lindblad part simply refers to the fact that we're going to use a Lindbladian, where we are going to assume that this Hamiltonian is 0, and these Krauss operators here, or Lindblad operators, are just going to be the Paulis with some rate lambda. Okay, and so the model can be written rather simply, but it still is not great because the number of terms here is going to be 4 to the n. You have 4 to the n different Paulis that you have to consider, therefore 4 to the n different coefficients. So how do we deal with it? So the way we deal with it is by sparsifying it. We consider each qubit and we say, okay, they are going to be single qubit Pauli terms corresponding to the qubit. And there are going to be connections in the hardware that are already present where 2 qubit entangling gates can be done. And they are going to be 2 qubit Pauli terms corresponding to that. But we are not really going to consider like what happens between, if we, like we're not going to consider 2 qubit Pauli terms between 1 and 7, for example, right? Only 1 and 4 and 4 and 7. Okay, so the pie chart here essentially shows you the 3 single qubit terms. This 3 by 3 block shows you the 9 2 qubit terms, and that's kind of it. So you can essentially bring down the scaling to a linear scaling with the number of qubits, at least on a linear architecture, going from 4 to the n. And that's what we mean by sparse. We're not capturing the entire set of coefficients. We're just assuming a lot of them are zeros. Yes.
Would you have to do this process like specifically for your hardware every time?
Yes. So you have to know what your device looks like, where the crosstalk between the devices are, right? And in fact, the learning process in order to determine the lambda case has to be done like kind of repeatedly, right? Like every 8 hours or every 6 hours, you need to go and get these coefficients exactly right because, you know, the device might have changed, right? And maybe one day we'll have devices that like, you know, once you capture it, it remains the same, but there are all sorts of physical processes we are doing to the device that is going to change its behavior. And we need to be very, very exact when you're trying to capture these coefficients to do zero noise extrapolation on top of it, because our goal is to first get the lambda case and then to increase them, right? So you have to be very, very precise. Okay. So how do we learn these lambda Ks? So the way we do it is we essentially start with some lambda tilde that we want to learn. And we say, okay, these are the terms that we want to capture. The terms are going to be all the single qubit terms and 2 qubit terms that are already connected. And then keep repeating that particular layer to see how the fidelities of the Pauli expectation values decays. And then you have the lambdas, right? So very, very straightforward, but does take a decent bit of computer science to be able to do it because you want to make sure that you are capturing as many of the coefficients as efficiently as possible. So this is one of the homework problems that I have submitted to Vivian, which is how many model coefficients do we need for a linearly connected device? The hint is just count the boxes and you will see how it scales, okay? So that's why this picture is here. This picture is supposed to be the hint to that for that question. Okay, so let's move on to probabilistic error cancellation. Probabilistic error cancellation essentially aims to first learn this lambda, which we said we will first assume that it's a Pauli model. After twirling, make a Lindbladian model out of it, sparsify it, right? And now and then we go ahead and repeat the layers over and over again to get the lambda case. And now we want to cancel the lambda case. We don't want that error to be there anymore. How do we do that? Well, writing the lambda inverse is rather straightforward. Implementing it is quite difficult because for one, it is not a physical channel. Lambda is a CPTP channel. Lambda inverse is not going to be CPTP. Okay, so it cannot be physically implemented, but there is a trick. And the trick is sampling. So let me show a very, very simple example of how we might do probabilistic error cancellation on a single qubit where there is really nothing going on, just identity operation, but the identity operation is faulty. Okay, so let's assume that my original channel is lambda 0, which is a bit flip channel with the bit flip probability 1 minus p. And I want to apply lambda 1, which is what I get to control, and it has 1 minus q as the coefficient on x, but it is not probability because, as you will see, q is not necessarily a positive number. And that's why lambda 1 is not a physical channel. So if I was to compose lambda 1 with lambda 0, you will see that in order to get the x terms to be 0, I would need q to be minus p 1 minus 2p. If p is a positive number, then q is not. So how do we exactly implement lambda 1 if it's not a physical channel? The way you do it is first you implement just the channel with probability proportional to absolute value of q. And then you introduce an error, right? So what you're doing here is you're deliberately introducing a bit flip on your own. You're just doing an x before the channel, but you're controlling the probability with which that happens, right? And so with probability proportional to absolute value of 1 minus q, you implement this circuit. You keep track of the signs. So you say, okay, whatever measurement I get, result I get here has a sign q. This one has a sign 1 minus q. And then the expectation value is essentially going to be the summation of the results that I got from before, but I have to keep track of the signs. And when you do this entire thing, it will be the same as, well, at least effectively, applying lambda inverse. So what that means is instead of doing just one experiment, now I have to do two and then combine the results from the two experiments in order to do the cancellation. Okay, and so that's the trick for doing probabilistic error cancellation. Probabilistic error amplification essentially has to do with the same thing, but now we want to increase the errors, right? Instead of canceling it, I actually want to increase it. And that is another homework problem, is try to figure out how you would solve this equation if what you really want to do is not make the probability of a bit flip 0, but actually make it like twice as much as before. Okay. Probabilistic error amplification then is essentially you'd want to double, triple, or amplify the noise. And why do we want to do that? We want to do that because then we can do zero noise extrapolation back to the value that you want, right? Okay, questions? Yes. Oh, I have written down the homework problems. You should be able to get like a decent text description for it. Yeah. Okay. I feel like I did good on time. I wore you guys down. Good. Finally. So what does probabilistic error amplification entail? Well, it entails everything we talked about so far. Because you have to do dynamical decoupling in order to get the noise model to be Markovian. You have to do Pauli twirling for it to be a Pauli model. You have to do measurement error mitigation in order to do any of these things, even to do the learning. Then we go ahead and learn the sparse Pauli noise model. And then we are going to amplify it. And then we are going to extrapolate it back. Okay, so there is a learning step. Error suppression is happening throughout. Learning step for the mitigation and for the rates. And there is going to be amplification step. And then at the end, there is going to be an extrapolation step. Okay, so yes, yes.
Hi. So in noise extrapolation, you said that you'll double the noise. I want to know how are you quantifying that increasing some amount of noise is doubling the effect?
Yeah, so you have these model coefficients lambda. You can show that you essentially multiply those coefficients with some parameter alpha, and that has the same effect as doubling the noise. Or not doubling the noise, but scaling the noise by alpha.
So do you scale it multiple times to extrapolate basically?
No, what we do is we do this sampling right here that we were talking about before, where you inject the noise, where you know what lambda is. Now you know what probability with which it experiences a bit flip error. Now I'm going to introduce more bit flip errors in certain circuits, knowing what the probability is supposed to be in order to do the amplification. So I'm going to, let's say I had in this bit flip circuit, there was, instead of a single circuit, there were multiple circuits. In a larger case, there are going to be a whole bunch of different Pauli terms. And so every time I implement the circuit, I'm going to choose a certain Pauli from my probability distribution, which corresponds to the amplified noise. And then I'm going to run that experiment with that noise injected.
Okay, thank you.
Okay.
Can you do this with every channel that you can imagine? So this is the bit flip noise, but I don't know about the amplitude damping or like some other more complicated.
If you have a Pauli channel, yes.
Yeah.
If you do not have a Pauli channel, I think it's going to be very complicated.
Okay.
I actually don't know if you can even do it. This is the whole thing is simplified because we're only considering Pauli channels and we know exactly the rate at which the errors happen, right? So that was the whole point of the learning step, right?
Yeah.
If you do not have a Pauli channel, I actually haven't thought about that.
I remember one of the homework problems that I was assigned along, like they want to try the depolarizing channel, and I think you can do it, but
yeah,
the
depolarizing
depolarizing channel is like really symmetric, you know, X, Y, and Z, but I don't know if you can
It's
do
a
it.
subcase of the Pauli channel.
Yeah.
Depolarizing channel is the Pauli channel with all the coefficients being like uniform, like the same across all the Paulis.
Okay, thank you.
Yeah, so that's why it works. Yes.
Q equals minus P or 1 minus 2P
Uh-huh.
for the general case?
Yes.
Okay.
You should be able to get it. If you look at the PEC paper, probabilistic error cancellation paper by Ewout Vandenberg, I'm sure. Well, not go to the supplemental material.
So you're saying like just in the end, all you need to solve is a linear system. Or does it involve any complicated equation for P, for example?
I don't think it's that bad. I think there are more complicated linear equations, even in terms of mapping the coefficients to just getting lambda case. I don't think this one is that bad.
Okay. Yeah. Thanks.
Yeah, because you're only using you're using that sparse Pauli matrix, right? A sparse Pauli Lindblad model. So there really aren't that many terms, and so it's not going to be that bad. Like it's going to scale linearly with the number of qubits, so you don't have to worry about it as much. Okay, so. Questions?
So about M3,
Oh, yeah.
from my understanding, it's a mixture of both assumption and empirical data. And so I assume it's specific to the problem and specific to the hardware as well.
Yes.
So what is the trade-off of using this technique when you're trying to do error mitigation?
With M3, because you are making certain assumptions to not have to deal with the exponential matrix, but those assumptions you can argue are like, well, you have a hyper parameter there, right? Like you want to consider a subspace reduction, but how far in Hamming distance you're going to go is kind of something you want to use. And you also want to have like some kind of precision bound saying like, I don't want to track terms that are like more than like smaller than, you know, my 1 divided by my number of shots or something. So, but even then it can take a while, right? Like, but not, if you are at 100 qubits, it can take like a few minutes, like sometimes maybe even tens of minutes to be able to get the mitigated result. And so that's the reason why we are using T-Rex now, because that has, the post-processing step is much shorter, okay? But M3, you are not really going away from the exponential overhead. You're just like strategically trying to reduce it. But how far you get kind of depends on how precise you want your result to be. Yes. Yes.
Thank you. Just wanted to verify how you amplify the noise. Do you just apply the same gate multiple times?
No. That is one way of doing it. That is called
Okay.
digital Z&E, applying the same gate multiple times. The way we do it is by doing the sampling. We know at what rate certain Pauli errors happen. So when we run the experiment, we take a circuit and we say, okay, we want this to have amplified noise. And so we start with, let's say there's this bit flip channel, and instead of just doing I lambda, I'm also doing X lambda. I'm introducing a bit flip error, but I'm introducing it at the rate of 1 minus Q. And so therefore I can control the rate at which I introduce errors. And the way you do it, maybe I have a plot here, is let's say this was your circuit right here, right? You see, I was doing these twirling steps here. I would also add an extra step down here to be able to inject the noise. I just add like a random Pauli drawn from a distribution. So you resample over and over again.
So that model allows you to say that noise is linear.
The model allows you to say the noise is linear because the entire description is a Lindbladian. And so in order to increase the noise, you just have to take these lambdas and increase these lambdas. So you learn what these lambdas are and then sample from the increased lambda distribution.
Okay.
Right, so because we know precisely what the noise it's captured right here. We will learn exactly the lambdas. We know exactly what coefficient each of P of K has, and therefore we can amplify it.
All righty, thank you.
Yeah, so the learning step is very, very necessary. A question? No question, okay. So with 4 minutes remaining, hopefully this figure now makes sense. Let's go through it. The random circuit instances are the Pauli twirls, right? You're trying to measure some observable. You keep doing various twirls, it converges to a certain value. G equals 1, 1.2, 1.6 are the 3 different amplification. G equals 1 is your original experiment. G equals 1.6 is the one where the noise has been amplified 1.6 times, therefore you see the results are worse. You take those points, go to the second graph, now you extrapolate. You can either extrapolate using a linear curve or an exponential curve. That gives you this 0 value right here, which is going to be your mitigated value, right? And you do it for a whole bunch of expectation values, which is how you get this average magnetization, which the unmitigated was quite worse. The mitigated one is quite close to 1. And in order to do this, as we talked about, you have to do dynamical decoupling, you have to do twirling, you have to do mitigation, you have to learn your noise model quite well, and then you have to go ahead and run the amplified versions and then do the extrapolation. Okay, I actually am done. Okay, 3 minutes questions. You have a question here and a question there. Yes.
How do you have control over G again? Sorry.
No, we have control over G because we learn the noise model very, very well, right? And once we learn the noise model very, very well, we are going to amplify the noise by injecting extra polys, right? Which are drawn from a distribution.
Yeah.
And the distribution has the rate at which you should apply that poly, which comes from the noise model that we learned. Okay. So again, let's go back to wherever that plot is. Where is it? Yeah, right here. This is your equation. Each P of K has a coefficient e to the power minus 2 lambda K minus 1 over 2. We know lambda very, very well. So we know the rate at which PK is the error is supposed to happen. Now I want it to be 1.6 times something. You go back to this equation right here. You say, well, I already know for a very long equation what the various P's are. I want to introduce a Q so that it becomes like 1.6 times P or something. I solve for what Q is, then I decide how do I add the noise accordingly. In this case, we're doing probabilistic error cancellation, so we're trying to get it to 0. But to amplify it, the process is very similar. It's just you need to know those rates very, very well. Okay? There's a question here.
Thank you.
I was curious about the Pauli-Lindblad noise model. So my understanding is that the norm is to think of that in terms of environmental decoherence, where you're sort of losing the information about the superposition because it's washed out due to interaction with the environment. I was curious, can you put something like continuous spontaneous localization in instead, where you're actually collapsing the superposition rather than washing out the information with the environment?
You could do that, but how do you do it scalably, I guess is the question, right? This particular model is nice for various reasons, right? One is that because we can go and learn the lambdas very, very well, but 2, also because we can amplify it. So if you consider a different noise model, which might be more accurate, but maybe is not necessarily Markovian, I think it introduces all kinds of complicated. This whole thing is kind of with error mitigation in mind. So one thing I would emphasize is that it's not necessarily true that that is the noise model for your device. We already twirled. So that is not exactly how your device works. It's just a very good approximation that works on average. Okay. So, and a lot of times people will confuse the two. They'll think, oh, I have a noise model for the device. Well, on average, but not exactly. Okay. That's not a physical noise model. Yes.
You do dynamical. So we start with doing dynamical decoupling, and you said that that removes non-Markovian noise only.
Yeah.
Or, so in some sense, you're just using a Markovian model because you're assuming that the non-Markovian noise is already being suppressed.
Yes.
Okay.
Hopefully.
Oh.
Right? To the best that you can. But you're also doing twirling, so that should also take care of some stuff. Okay, it is 12. But if you have questions, you can find me. I have been strictly instructed to not stand between you and your food. So don't trample me. Thank you.
So this material and the hands-on section will continue this evening at the study session at 6:30 over at UT. So you'll get to do the programming part of what they're teaching. Thank you. We're going to post things just as soon as we get them.
Hey folks, quick update. Lunch is outside, so go and grab your lunch. It's salsaritas, Mexican style type food. The ORNL logo store is located underneath the staircase that you came up. There you can buy t-shirts, hats, pins. I'm not sure what else. If you want to stop by there.
Hey, sorry, I didn't get to a lot of the questions.
If you are in nano fabrication, you are getting on a bus after lunch and going back to CNMS. That bus will bring you back here by 3:30. The bus for UT leaves at 4 o'clock. Leaves at 4 o'clock. You want to be on it before 4 o'clock. Okay, that's it.